Good morning. Good morning, everyone. Today we are again going to look at a new topic, or let's say related topic, what we were talking about. And today we are going to look closely into what is memory wall, right? And so the question we are asking is basically that when we are trying to build a system where we have our computing units, right? Our GPU or CPUs, we have our memories, which we are having, right? Which we want to put on so much memory, which is required by these AI systems, right? Because they are going to drive at least the advancement of technology, which we see as of now, right? And you see that this memory and the computing unit, they are talking to each other. Computing is computing whatever you want to compute, right? And then there is an energy consumption, which we say that which is happening in a data center, right? And the question we are asking that if these kind of computing, which we saw is like a super chip, right? In the if you saw the last video where we were talking about that different levels of interconnect in an AI system or in an AI data center. This is a super chip which sits in a computing fabric, right? Which computing fabric is on a board which sits, let's say, on a rack, right? Because rack server or what we call as the racks, and these racks have these boards or this computing fabric which has multiple of these super chips, and these racks are ones which are sitting in your data center, right? So that is the kind of hierarchy we saw in the another video that what is, but in the end which you see is this super chip which we are talking about. Super chip means it's a combination of chips, right? Like memory, which we say M, is a HBM for AI system, which is the high bandwidth memory, right? And this itself is a stack of chips, right? It's multiple DRAM chips or silicon chips which are put on top of each other, right? That is what this guy or this cube is having, right? And there are two important companies who have been making these chips, one being SK Hynix and another is Micron. Right. So this is the DRAM technology which they are using and putting them in a this kind of fashion, which makes this memory, which is a part of your super chip, right? Which you see. Another is the computing unit, which could be a CPU or a GPU, right? And these obviously the one of the very famous operation which you see in the AI is when we are looking at is the MAC operation, right? This kind of operation, right? Where you are multiplying each input with certain weights, and that is what is making these neural networks, right? So there is a addition, there is a multiplication which is going on, and then there is a addition which is there. So addition, if we see, is a very much the fundamental operation of a digital system, because with addition we can make subtraction, we can make multiplication and other operations, arithmetic operation with this addition. So this is a very, very important operation. So now we just taking this case, we will try to understand that how much energy actually is spent when you are computing, right? But let's say when we are computing, we are also talking to memory. So there is a interaction which is going on between memory, which is what we say as the data throttling, right? Um, or data transfer, right? That means data which is transferring from this is paying certain tax at certain places. So we are going to basically look at some rough calculation so that you get an idea that when we are designing such a system, when we were talking about integration and have a very close integration, you kind of appreciate what is happening in this domain and what could be the future chips. If you are in this business of designing this future chip, you may get that inspiration. Okay, this is an interesting problem, let me look at it. And if you find any difficult to get started, please do contact me. I'll be more than happy to provide you resources to start some of the things. Though there are many papers you could find in the relevant domain, and as much you would read, you would have a better sense of the problem, and then you will be able to better equipped to actually solve the problem, right? So that is what, and this is going to become more and more exciting in future, where we are entering an era where demand of the AI model, what computing demand, is much much more than what we can provide as of now, right? So that means there is going to be like that you have a lot of pressure on the hardware to be much much better, right? And hardware, typically the innovations in hardware always are slower, but at this point of time, the industry is really really looking at this point, trying to use the AI actually to design these chips also, right? Because there is a very interesting exciting times we are entering. We don't know how the future would look like, but one thing we are sure, that humans are going to put everything on the table to make that more and more efficient, right? So that is the idea. We are already talking about in the, where we have to power a data center like AI data center, you may need a lot of power, which may not be provided by grid only, and you may need like a nuclear power station, right, to power this kind of thing. So that means you really need a lot of uh, power to enable this kind of AI data center, because it's so power hungry or the energy hungry. And now we are going to see much deep down and what is happening when we are moving this data and we are computing, right? Because we saw this computing fabric is like the, how do you say, the heart of it, the data center where everything is happening. The other things are just connecting them together, right? And we saw in the last few videos the different level of interconnects which are there in this system. So now the question is, okay, if the computing, which one is taking more power? Is it by computing or is it the moving data? And let's take some few numbers and few examples so that you can kind of appreciate what is happening. And that I would suggest with everything which you do, typically, please do take into account some of the rough calculations can give you sometimes very very interesting insights. So do that, right? Don't be fearful of doing those, that you make a lot of assumptions, it's okay, but you get some numbers so that which can give you some sense of what is happening in these systems. Okay, so let's take an example of a computing system. And a computing system, I think we already talked about addition, so we can take an example of, let's say, a 32-bit adder, right? Which so 32-bit adder, which are made with, let's say, the different bits of full adders, right, together put in, and that has a simple adder. We know that it has certain gates, and each gates has certain transistors, right? So in total, we could say that this could amount to, let's say, if you were to design, it could amount to um, transistors, yeah, amount to 500 to 1000 transistors, right? That is what is there, let's say, in an adder. Okay, so this is what our computing is happening in this. And then this, there is a DRAM, right, or memory, which is external memory. And this, it finds, okay, there is something missing, or it has to store the data. There is an interaction which would happen, and we know that within the chip also there is a memory which we know as SRAM or cache, we have talked about, right? So that means there is obviously tendency to first go to the cache, but you is limited. We know that cache, the sizes which we are talking about in computers, if you see in your laptops, we are talking about 60 to 16 to 32 GB of DRAM, while cache we are still probably talking about some MBs, right? Let's say 8 to 10 MBs, right? So you can clearly see the demarcation or the difference between this cache sizes, like it's a orders of magnitude lower than that. So obviously you would not find every information in the memory, or you may not be able to save every information in cache, and you have to use this external memory, which is this DRAM or HBM cubes which we are having, right? So now let's look at first what is happening in adder. Once when you are adding, how much is the computing energy you are spending, right? And then we have to take some numbers. So first of all, we take, okay, this technology or the transistors, when we are making this function, is implemented using CMOS. In CMOS, we know the energy is basically, because it's coming from the CMOS circuits, it's dependent on alpha C VDD square. That is the generic number. You can easily see it from a NOT gate also, like a CMOS inverter, which we talked about also, where you see that this depends on the activity of that block, right? How much it is active. Then this is the capacitance which you are having of these transistors, right? And this is the VDD, or the supply voltage, which you are using for these transistors. Okay, and we are going to take some numbers which are, let's say, for 3 to 2 nanometer or 3 nanometer, N2, N3, which we talk about, right? 2 nanometer node or 3 nanometer node, which we are talking about. So we are taking, let's say, VDD is around 0.7, though it may be 0.65 also, but that is the range. So let's take 0.7 volt, right? This is the at what voltage your transistor is working in these chips, right? Now capacitance, how do we calculate the capacitance, is a very interesting way to go about, is from some knowledge of the MOSFET. So in the MOSFET, we talked about this capacitance is basically coming from your gate, right? Because there's a capacitance there itself in a metal oxide, and this oxide is what is driving this capacitance, the thickness. There's a length of this, and then there is a width of these metal lines, right? So if one was talking about gate capacitance, it can be seen as epsilon, which is your epsilon ox, into your area, which is W into L, and divided by whatever is your T ox. Right. As of now, we are talking about EOT of around 0.8 nanometer. Right. So that is the kind of where these transistors. So it can, yeah, I mean, it is still aggressive, but that is what the range we are talking about. So if we talk about that and we put in some numbers, right, A54 10 power minus 14. So let's calculate in, yeah, so that we can calculate in meters. So this is minus 12 then. This is, so width, let's say take around 50 nanometer, right? So that is 10 power minus 9. And then we have L, which is around 20 nanometer, right? So for these, there are some assumptions we are making, but they are not very far from the real device, which you will see. And EOT, as we discussed, 3.9, and EOT is around 0.8, right? So okay. So when you do this calculation, then you figure out, you may get your capacitance, gate capacitance around, let's say, around 0.05 femtofarad, right? That is the capacitance. But the one thing we have to look at, this is the only this capacitance we are talking about, right? And as we see, when we are connecting these with other wires, which are going to come like source and drain, this is also metal, this is also metal. There are other parasitics which are going to come in the device itself, right? So they are going to be there, and this is why we say this is just the intrinsic capacitance. If we want to take the total capacitance of the transistor, this would be intrinsic capacitance plus the parasitics, right? And let's take some parasitics which are around, so 4 to 5 times of the intrinsic capacitance, because parasitics are really, really dominating. So then we can get maybe about, so your capacitance could be about 0.1 to 0.2 femtofarad. That is the range you would see your capacitance will come. And so this is per transistor, obviously, right? So then if I were to calculate energy, now I have to put in numbers. So first of all, oh yeah, activity also I have to talk about. Typical activity, let's say in logic circuits for this arithmetic circuits, could be around 0.1. So we can take 0.1 as the activity, 0.1. Then the C is your, what is your C? It's a 0.1 femtofarad. So 10 power minus 40, 15. How many transistors? 1,000 transistors, let's say, right? And then we have VDD, which is around 0.7 square. So you can do the calculation and you would be able to see how much energy. So let's take this in femto, right? So femto is there. And then this would be in joules, right? So femto joules, then 0.1. So this is 0.1 yeah, 0.1. So this would be 10 into, this would be 0.49. So that would be around, yeah, 5. right? 4.9. So 4.9 is like 5 femtojoules is your energy which you are going to spend while doing this addition operation, right? So that is a very rough calculation, but it gives you some idea. This is what the energy you would spend, right? Now let's look at, okay, if you were to now shuttle the data, right? So you want to find or let's say transfer the data from DRAM or to this, how much would you spend or how much energy would you spend in data moving or data movement, right? So for that, you know this data movement is happening through copper interconnects, right? Right. And in copper interconnects, the typical range, so this can be also seen that we can find would be around, let's say, for our technology, when we are looking at this, would be around point 0.1, I think, femtofarad per micron, right? And this comes out of from your unit of, let's say, when we are talking about in the interconnect, how much per micron you are having in your or due to your so this could be a 0.2 femtofarad per micron, or we can write in picofarad, sorry, it would be picofarad per centimeter. How you would get it, it's from the interconnect. Let's say, let's think about the interconnect. So interconnect, as we discussed last time, it is a copper interconnect which is going like this. There's a length of the interconnect, there is a width of the so this is the, sorry, the thickness or the height of the interconnect, and this is the width of the interconnect, right? And then when we are writing the capacitance is again the same. Let's say whatever your epsilon naught and the whatever is the permittivity of the dielectric which are there, right? Which is, this is surrounded by dielectrics, right? Uh, right? Typically SiO2 or any low-K dielectric. And then we would, because we want to reduce the capacitance, and then we would see that this is your length and yeah, so area divided. So this is basically, now we are, when we are taking is the height of this, because there is a ground plane, right? So we are finding this capacitance which is with the ground plane. So that means now we are going to have L into H, sorry, L into W, and that is the interface which you are having, and this is the H, the height defines the H. So this is your L into W is this plate, right? So this plate, how much height it has, based on that it would have this interconnect, right? So this would be, then we will see that if you were to calculate per length, it would be something like epsilon naught XLR R divided by W by H. If they are nearly same, right? So if it's a square, for example, which we can say that they are same, then we can see this is just, right? So that you could see that would come out to be for a particular, so let's say epsilon R, if we take it to be 3.9, so you would get this value around 0.2 femtofarad per micron. That is what I was quoting, right? So this is the interconnect, basically capacitance, which you are going to see when you are moving the data. The question is, how long is this interconnect? So this interconnect could be very, so let's say when you are going throughout the chip, right? This is going to the system. So let's look at the system, right? You are going from this part, let's say this pin, to another pin in the DRAM. So that means that this could be, and I'm taking a very optimistic number, it could be the length of the interconnect could be about, let's say, 1 millimeter, right? Very again optimistic number, right? That this could be more depending on where are you, how far it is placed and everything. But that this is the number. With that, if we go, we can calculate the total capacitance, right? So total capacitance would be 0.2 femtofarad into 10 power 3, right, micron. So so from here itself, you can see 200 femtofarad is your capacitance. And if I were to calculate now energy, which is again C VDD square. So C is this, VDD is zero point 0.7 square. So this is your femtojoule. So you see 200 divided into 0.5, right? So that is around 100 femtojoule. So you see your energy, which you are taking to just throttle the data, is around 20 times more than what you get in the transistor, right? So that itself tells you that computing, so basically data movement, right, is the bottleneck. Movement uh, basically drives the energy bottleneck. Right? So this becomes the, or it drives, basically it becomes the bottleneck. Yeah, data movement becomes the bottleneck for reduction or reducing energy. Right. So where we see the computing, you may spend lesser energy, but because this is the problem, that's why you see that designing the best CPU is definitely important. But if you see, the system design becomes much more critical in designing that. In it's basically reducing the energy, and that is why we saw one of the solution to that was where you are putting the computing basically and the memory very close to each other, right? So let's say on top of each other is a very close where you don't have to run, and these interconnects then are very short, right? So this length which you were spending, let's say millimeter there, so had thousands of micron, this could be around, let's say 2 to 3 micron, right? Or so few microns, let's say. All right. So that is the range. So you already see that you would be able to reduce your energy 100 times if you do that, if you come into this range of arranging that. But there are different pros and cons, right? This is the pro, that if you reduce this interconnect length, right, reduction in L interconnect, right, obviously that gives you very low energy for data movement, right? So then, okay, now you are talking. Now the data movement is not the bottleneck if you could arrange the system like that. So that is what industries are looking at right in the future or now. And there has been a product, I think, by AMD, where, as I was talking about in one of, where they integrated the SRAM die on logic, right? So there was this demonstration where logic die means which is doing the computing, and the SRAM chip was on top of each other, and this was done using some interconnect which we know as hybrid copper, which was like state of the art interconnects, copper, hybrid copper interconnect. So this has been demonstrated by AMD. I think, I don't remember the exact model, but you can look at this SRAM on logic die demonstration, right? So that's been very interesting, the way the field is going, and there's a lot of scope still, because we don't really, in the end, the main thing is to what is the limit of it, right? That is what one would talk about, and this we would also see in probably one of the video. What is the limit of computing, right? When we are doing this energy transfer and everything, what is the limit actually? And that, one of the scientists was thinking about this, who is called Landau, and he was thinking about, okay, what is the computing limit, right? When I'm, let's say, writing a bit or erasing a bit, where do I lose the energy? And so all of that we will talk about in another video. But for now, our goal was to come up with an understanding that, oh yeah, data movement is the real bottleneck in the energy reduction. And then if we want to do that, we have to put that in this way. But there are other disadvantage which you would get if you put these memories like that, and which is because your logic die, it generates heat. As we saw, these transistors, they are doing computing, heat is there, and if heat passes to your memory, then there is again a problem, because if you remember your memory, let's say this was a DRAM memory where you have your transistor and you have a capacitor, right? And let's say there is a heat coming in, which is coming from your logic die, right, to these cells, the DRAM cells. You see, the temperature does not really fare well with the semiconductor, and the semiconductor starts seeing more leakage, right, as the with temperature. And when there is more leakage, that means that you lose the data in DRAM, or the DRAM integrity becomes very problematic with if you are doing this kind of heat transfer. So then the question comes, how do you redesign? You have to probably look at, let's say, the refreshing you have to do more often in the DRAM, which we saw obviously because of this leak we have to do, or we have to think of some other different kind of memories where this leakage may not cause this kind of problem for when we are putting, let's say, logic and different kind of memory dies on top of each other, right? So that is where the field is going. The things are becoming very multi-physics, multi-scale, which is what I am mostly interested in and makes me very, very how do you say, excitement is intact after even working in this domain, as I have seen. And when things turn this multi-physics, multi-scale, it becomes much more interesting. And I think that is what my observation has been about the semiconductor industry. When we look at this whole thing from integrable, or let's say very integrated approach, things look much more interesting, because then we understand what we do on a daily basis. Let's say we focus on one part of it, because obviously when you are doing physics, you or any kind of innovation, you focus on just one part, taking the consideration, let's say, of whatever it is interacting with, and then you see how do I make that better, right? For example, if this is the DRAM, and in this I say, okay, the temperature is affecting this transistor, then I say, okay, how do I make this temperature better so it is more temperature intolerant, right? Or it is temperature tolerant, in the sense that the leakage does not go very shoot up with the temperature. Can I make this like uh, transistor with some other alternative technologies where temperature does not dictate the leakage, like how in the normal transistor we see that where you have the over the barrier transfer, or your thermionic diffusion or thermionic uh, transport, which happens when in the off condition of your MOSFET, right? So that is what one would then go into and spend your time into. Okay, what can I design? How do I design this transistor? And that may not only affect this part of DRAM, but it can really have a wider impact, right? And that is what brings the whole interesting part, that academia keep doing what they know how to do. And then after talking to industry, and when you are working, you could really make a very interesting technology which can be used or can be implemented within the real products, right? So that is where silos, I would not also say it's good, but it is, yeah, at least I see that there is a lot of interaction with the industry, does help us think about the problems much more clearer. And it does give us some understanding of what are the real constraints in the real product when somebody is implementing them, right? So that knowledge does help in really coming up with new science when we do. Okay, so that is what we talked about. And thank you, and I hope you enjoyed this part of looking at that. Really, the energy is very much dictated by the movement of the data, and that's why a lot of different things which are happening. And one thing we didn't talk about, but let's say let me just take a few minutes and talk about it also. So let's say when we are saying that logic I want to do and this memory is far away, right, where I have to shuttle, one thing is I can put them on top of each other. Another question could be, what is stopping me from putting this logic inside the memory, right? So that means if I have a memory, is it possible to put this kind of adder, right, or adder units inside the memory, right? And that is what is the field which is evolving also, is called in memory computing on program in memory, right? So this you can explore also if you are interested, where the idea is now how do we compute within the memory, right? Whenever there is a requirement, that means my adder does not need to be separate, physically separate from the memory, and it is very well part of the memory, right? So that brings another kind of innovations which are going on. And somebody can ask the other question also, what is stopping me from putting the memory on logic, which is what you were doing here, kind of. You were basically reducing the distance of the memory and logic when you put it in on top of each other, right, kind of. So there are multiple ways you can think about these problems, and all of this leads to a new area of research which is going on in the world. So that was the whole idea of last few lectures, which I thought that I should tell you about what is going on in the world and what is the rationale of looking at those problems, right? Why people are looking at those problems. We can delve into different technologies of memories at some point. That is the DRAM the only technology, or are there some very potentially interesting technologies which could really, in the end, it's the interplay of the memory and logic together, and we have to probably rethink the memory also, that how the memory cells would be made, right? So all of that is also a very, very much part of what is efforts of different companies and different people or academicians around the world, right? So that is something we can talk about in future videos. So thank you, and happy growing, happy learning to all of you, and see you in the next video. Bye bye. Thank you.